very much. This is just many copies of this for every momentum mode Q. When I said this was an analogy of this, and don't waste my time, you write it out yourselves, that was based on this part. It's only the operators that have this relation that have this relation. So remember, I was inserting these states like crazy and using that fact. That fact is tied intimately to this fact. This fact is in perfect analogy to this fact, which is in perfect analogy to the both statistics I chose here. If I don't have those statistics, I don't have this relation, and I don't have this relation, and I can't do what we did before. So that's where it leaked in. And indeed, you can say, look, guys, this is just a quantum operator. I can put in interesting intermediate states and try and get some sort of... It's a shame that A, time is short, and B, that I would have to bring it back to memory or redrive it. But I'm about to give you the slick answer and prove that it's correct. And that's a terrible way to learn. The right way, which takes 10 times longer, but then you become 10 times smarter, is to try and not know the slick answer and try to sort of bang this out by putting in honest, complete states, complete sets of states like this in some way, and try to see what happens. And then you discover that the slick way of doing that, but honestly, you do it honestly, and then the slick way of doing it turns out to be the slick thing I'm about to show you. It's a shame that one can't do that, but the place to learn it, you must learn it, because otherwise life is not worth living. In a good condensed matter, sort of, or StatMag, a little bit advanced StatMag course, there's the process of turning very C-number problems. You know, the Ising model of StatMag never mentions a fermionic operator. It's just a bunch of numbers which are plus and minus 1. It doesn't get easier than that. And yet, problems like that can be converted, A, through the analogy between statistical mechanics and particle physics, or quantum field theory, that hopefully Rashmi mentioned to you, and 2, by sort of the honest version of what I'm about to show you, or rather, not honest, the sort of the lowbrow version of it. Shows you how you create operators like this from completely C-number plus and minus 1s. It's very beautiful, very powerful, and it's a way of using quantum field theory to solve hard problems in statistical mechanics. And run in reverse, you can get great insight into quantum field theory problems conceptually by turning them into conceptually straightforward statistical mechanics. We don't have a chance to do all of that, but you should at some point. I think a little bit of this, if you're interested, is to be found. You know, I had a great set of lectures when I was a grad student, but somebody gave it to me. But the closest place I've seen, which discusses some of these tricks, I don't know if it's the best source. Maybe you should ask Professor Dashon or something. But is Itzikson? I forget how to spell Itzikson. And not Zuber, but Ruffet. So I think these tricks are discussed there. But it's in the spirit of your question. Okay. But I want to say that as a lawyer, within my rights, I've done everything right. Okay. Yes. So we want to figure out what this is and what this is, and where and what happens to this statistics. Okay. And so basically, I'm going to guess the answer and prove that it's correct, as opposed to make it seem reasonable and so on and so on. But I want to just say a few words to motivate why, in what sense, it's supposed to be correct. Okay? So even here, You know, here, phi hats at different space-time points, they don't commute, right? But the one thing we know is there's an h bar in them, that commutator. It's the essence of quantum mechanics that these things don't commute. And yet, somehow, when all the dust settles to the path integral side, you end up with objects which, for various reasons, don't have this feature that they actually do commute. These things can, you know, phi at x and phi at y do commute. They're C numbers. Similarly with these sources. In a sense, you can think of these as sort of two sides of the same coin, turning the problem, which is quantum mechanical, into something which is not, where the h bar is put somewhere else. Okay. The way you think of a source is like any good bad gadget, okay? Some macroscopic thing which, when all the dust settles, h bar happens to be effectively small for this device, and you can think of it as a classical approximation. Somehow the h bar is got rid of. When somebody says, I have a classical device, you're saying, you took the responsibility of making sure that the way this thing operates, the output is not very quantum mechanical. There's some pretty good 100% guarantee of exactly how it behaves. I'm not doing quantum probabilities. That means that somehow you got the h bar out of it. So this J is like some sort of collection of particles where you manage to get the h bar out of it. Okay? So magically, this is what happens in everyday lives, which is why we're not aware of quantum mechanics normally. Okay? Here too, you want some sort of thing which gets the h, but the fact is these things also do not commute in general. So, anti-commute. Okay. And so, in both of these cases, you can think of this h bar, it's gone to 0 somehow. Here you start with these anti-commutations of order h bar. And so you might have thought that here we should look for something where bar where it's 0. But this would still be a rather odd type of thing, because it anti-commutes to give 0. It's not like it commutes with itself. It anti-commutes. Okay? So we think that we should be playing around with a new kind of object, which instead of having a non-trivial anti-commutator, we should be playing around with fields where the h bar has been put into some other path integral way, but the basic objects that we manipulate in the path integral, sources and integration fields, obey this, this rule here. Okay, so that's motivation number one. The second thing, so these and similarly, these etas. By the way, I've been these kind of numbers. These kind of numbers from which we make these fields, meaning if I fix the space-time point, then eta of y is just a number, but not the usual kind of number that commutes with other numbers. It's something that anti-commutes with other numbers. So this kind of numbers are called Grassmann. I forget how many ends in Grassmann. Anyway, numbers. Indeed, when we think of adding a source term H equals H H source. So thinking canonically, we're going to want just generalize the notion of source term. That is some kick, some device that is effectively creating a non-trivial space-time dependent environment for our fermions. And so we would write it like this. Again, I'm using this kind of nice complex notation where well, for the moment it will be truly So we know that in fact we're dealing with column vectors, right? We have several components to a fermion field. So you're not surprised that instead of saying the word star everywhere, I'm using the word dagger. That's not a surprise. The gamma 0 is purely conventional. I could have just absorbed gamma 0 into the definition of eta. But because of the gamma 0 that comes into this other convention called psi bar rather than psi dagger, it is convenient to write the source term like this, so that instead of using star notation, of course we have to use dagger notation. And instead of using dagger notation, we are within our rights to use bar notation, where there's a gamma 0 thrown in, just as a simple convention, so everything looks like barred or unbarred. Okay? But basically, this is a simple generalization of the source idea, but for fermion fields. So, no big deal. The thing that would be odd is if this was just like J. If eta was like J, just a regular source, regular C number kind of field, then this Hamiltonian would have sort of Fermi statistics. It would have, if eta were a C number field like J, then H source would have net Fermi statistics. In other words, if I think of this eta as secretly some collection of particles which I'm just thinking of as a black box which produces, is a good gun for producing this psi. If this black box was just something like this J, a C number, then I would have an odd number of fermions in my Hamiltonian, which would already be a little bit bizarre. Remember when we talked about causality and we said the perturbations to the Hamiltonian at space-like separation should commute. Well, now they couldn't do that; they would anti-commute in some way. So it's clearly wrong-headed. And indeed, if I give you an example of such a source, okay, let's cook up. You want to imagine what kind of source could you have? Well, it could be that I'm very interested in An example. I'm very interested in top quarks. Just top quark. I'm interested in top quarks. And this is not how we actually produce them, but this is in principle we put it. I'm going to take a neutrino, an electron, and a let me take things easily found in nature. Okay. I'm going to bang these together, and indeed there is some small amplitude. I'm treating the weak interactions the way Fermi would have treated the weak interactions, just for simplicity. But indeed, I can think of this as a kind of a black box. I'm somebody who won't, let's say I'm only sensitive to these top quarks. I think of this as some black box that produces the top quark form. And this is sort of my eta. Okay, I have complete control of all of these ingredients. I'm very good at manipulating them. Maybe I should. Neutrinos are hard to manipulate, so maybe I should. Bars. So these are conventional ingredients. They're found in everyday tables and chairs. I'm very good at manipulating them. I tell you, look, I can make you top quark. You want a top quark gun? I'll give it to you. It's a black box. Don't question me on it. That becomes an eta. Okay? But this eta corresponds to some U d bar d. Whatever else, it's a collection of fermions, but whatever else, maybe it's a collection of fermions and gluons, I don't care. But in net, it's fermion. Okay? As long as the fundamental laws of nature are obeyed, the spin statistics theorem. So again, I'm treating this purely as motivation for saying we want something which is got this anti-commuting property, but something where, for whatever limiting reason of this device, it's very macroscopic or whatever, the H bar has been sucked out of it. There's no uncertainty related to the operation of the device. It will work as I specify. So we're interested in these Grassmann numbers, but ultimately this is not meant to be a motivational speech. Well, it is, but it's not meant to be the final thing. The proof is in the pudding. We want to see that a construction based on Grassmann numbers allows us to write a path integral which exactly matches the canonical construction. If it does that, then everything I said is fine. Okay. Now, it's very odd to think of numbers that anti-commute. In what sense? What type of object is that? We've heard of real numbers. We've digested complex numbers. What kind of number is this? Okay. And indeed, you have seen numbers of this type before. You just may not have noticed them. So I'm going to consider two Grassmann numbers, eta and eta prime. Of course, I actually want an eta at every space-time point. So that's a heck of a lot of Grassmann numbers. Every one is separate. But I'm just going to consider two eta and eta prime, as if it's like eta of here and eta of there. Okay, that's it. So here is an example. Take the Dirac matrices. In other words, the quick answer is, who are these Grassmann numbers? They're matrices. Okay? So here, take calling it gamma 4 in the Euclidean sense, so if you want, this is just gamma 0. If you just use the standard commutation relations of Dirac matrices, you'll quickly see that eta squared is 0. If a number anti-commutes with itself, then its square must be 0. So, if you want, this is a half. And eta prime squared is similarly 0. And even eta prime is 0. Okay? Just think about it. You'll see that just from the Dirac algebra. So here, using these 4x4 matrices, I have managed to create for you two Grassmann numbers, eta of here and eta of there, which obey those things. Now it turns out that if you wanted eta of here, eta of there, and eta of somewhere else again, eta in the middle, you slowly have to make the matrices bigger and bigger. So that, in general, the matrix representations grow like something like 2, since it's exponential in the number of space-time points. So if you imagine discretizing space-time and working in a finite volume, so you have 10 to the gazillion points, e to the 10 to the gazillion square-sized dimensional square matrices could be used to represent these Grassmann numbers just fine. And all the numbers in these gammas, of course, are just C numbers. It's easy, right? So there's nothing, there's no voodoo here. It's all just C numbers. But we would be struggling to manipulate these C numbers in a way that it would be hard to work with these very large dimensional matrices. So we want to just use the properties of the matrices. What's the defining property? It's just this. So that's where the slight level of abstraction, we're just talking about Grassmann numbers and not saying, look, tell me, I will not believe that this number exists unless you write it down as a matrix of C numbers. Once you understand that you can do it, forget about it. Yeah?
Do we multiply the Grassmann number by a real number or anything like that to give it like a size? Or?
Yes, let me go through that. But it's, when you think matrices, you already know a lot of the answers. You can multiply these square matrices by each other. So, for example, even though eta squared is 0, just because of this, it has to anticommute with itself, like it anticommutes with everything. And eta prime squared has to be 0. And even eta prime anticommutator has to be 0. But eta prime is not 0. Okay? There's no relationship like that. Anything that does not follow from those commutators in general will not vanish. And so you know what you can do with matrices. You can multiply them, or you can multiply them by a complex number. And you can add them. So all of those things are still true. Let me write those things down. Question?
So in the limit that there is a, you need an infinite number of these Grassmann variables, and so you're needing definitely infinite dimensional matrices. Is there some, an infinite dimensional matrix is like a linear functional. Is there some way to think of a Grassmann number as like a linear functional in some natural way, or just in a horribly awful way?
I think it's a horribly awful way, but I'm not educated enough to know if there's sort of a different way of putting it. What I would say, going back again to the thing that I think matters in your education, which is the StatMech side of the subject, is if you actually want to see, gosh, the funny thing in the StatMech approach, or rather, these things where you start with the Ising model and then you find yourself dealing with fermions in the continuum as some approximation for long wavelengths, is you actually start with a setup where you do see matrices that are huge as part of the problem that you're being handed. Okay? There's something called the transfer matrix in statistical mechanics and so on, which is a very, very big dimensional matrix. And starting from this horrible matrix problem with tons of entries and numbers, you convert it into a story of Grassmann numbers, and that makes it much, much, much simpler. But truly in the continuum, I don't know the answer to that question. I don't know whether it was really like a derivative you could think of as a kind of glorified matrix, right? In Hilbert space or space of functions or something. I don't know that that can be said here. But there is some axiomatization of these Grassmann numbers, and exactly how rigorous it is in the continuum, I'm not sure. What we're about to see is it's absolutely rigorous for perturbation theory, because perturbation theory is only about Gaussian integrals, and there's absolutely no question what the answer is. And even beyond that, I don't know that I care too much in the sense that I can always imagine discretizing, and then it's about ultraviolet sensitivity and normalization. Okay, I think we ran over time, so let me stop here. We'll take up this question. Tell me this before we stop. That last question in the homework involves Grassmann numbers and I think you can't do it, right? I mean, maybe you can if you already know something that I haven't talked about. I think you are not able to do that yet.
You mean the third one?
The third
We
one.
haven't given posted it yet, so we don't know what's on.
No,
The second homework, but the third problem.
Oh, the third problem, okay.
Which I thought was using a fermionic oscillator.
Yes.
Yeah.
I think you might not be able to do that. Okay, so don't hand it in.